All right. Good afternoon or good evening, everyone. So this is session S39, Navigating the Noise, Statistical Methods for Measurement Error in Data. I'm Sarah Latsbeach. I'll be your chair, and I'm really excited about this session today. So our first speaker is Dr. Lillian Bowe, who is a principal biostatistician in the Department of Epidemiology and Biostatistics at Memorial Sloan Kettering Cancer Center in the US. So would you like to share your slides? And then
Yes. All right.
I'll mute and let you take it over.
All righty. Can everyone see that?
Yes.
Yes. Okay, awesome. All right. Hi. Thank you so much, Sarah, for that introduction. My name is Lily. So this is actually going to be work that I completed as a part of my graduate school work in biostatistics at the University of Pennsylvania, where my dissertation work was focused on measurement error methods. And then currently I'm a biostatistician at Memorial Sloan Kettering Cancer Center. So I'm going to be talking about practical considerations for sandwich variance estimation in two-stage regression settings with applications in regression calibration. Okay. All right, so jumping into some background and motivation for this work. During my research in measurement error, I became super interested in different variance estimation methods that might be considered in two-stage regression settings. And a popular example of two-stage regression is regression calibration, which is a commonly used method for correcting biases in outcome model regression coefficients when exposure variables are recorded with measurement error. So basically, in the first stage, we fit a calibration model using linear regression to a subset of participants from the main study cohort. And then basically we use the stage 1 model to estimate the exposure on the full cohort. And then in stage 2, we fit an outcome model using that estimated exposure from stage 1, as well as other covariates in the model. Now, in two-stage regression model settings like regression calibration, additional steps are required in the variance estimation stage in order to make proper inference. Because in fact, the model-based standard errors that we would get from standard software are going to be too small because they don't take into account the extra uncertainty from the nuisance parameters estimated by the stage 1 model. So in this presentation, I'm going to outline the basics of sandwich variance estimation in two-stage regression settings, which we describe in our paper published in AJE earlier this year. And we did consider two settings for this work. Cohorts that can be assumed to be a simple random sample from the population, as well as cohorts from a complex survey design. But for the focus of this presentation, in the interest of time, I'm just going to focus on the simple random sample setting. But please check out our paper for properties, as well as a simulation study and a data example for the complex survey design. So for the case of data from a simple random sample, the bootstrap variance estimator, originally proposed by Efron, is a commonly used approach for variance estimation and for accounting for that extra uncertainty for the parameters that I talked about before. And now the bootstrap is often used because it's simple to implement and it's straightforward. But it does have some downsides, namely that the walled confidence intervals, which are commonly used, constructed using bootstrap standard errors, can be problematic. And I'll discuss this in more detail later. And this approach can require also extensive computation time since it involves resampling the data, refitting the models, et cetera. Now, alternatively, one might consider a sandwich variance estimator, which is the key topic of today's presentation, which is obtained by stacking the calibration and outcome model estimating equations. Now, I'll start by outlining the two-stage regression modeling approach using regression calibration as an example. Now, I mentioned before, regression calibration is a popular method for addressing error-prone exposures that's commonly used in nutritional epidemiology. And in regression calibration, we are essentially building a calibration model, which is our stage 1 model for X hat, which is defined as the expected value of the true exposure X given the error-prone observation or surrogate X star and the other error-free covariate Z. And we'll be able to estimate X hat if we have two error-prone measures of the covariate available in a subset. And I'll provide an example of what that looks like now. So consider a cohort study where in the main study, we observe an error-prone covariate, such as self-reported dietary intake, for example, recorded using a 24-hour recall. Now, self-reported dietary intake has been shown to be subject to both systematic and random error. So we're going to assume the following model here, which assumes that the true exposure X which is, for example, the true underlying usual dietary intake is linearly related to the self-report X star and other covariates Z, plus a random mean zero error term. Now, suppose we also have a second measure of exposure available in a sub-study. As an example, this might be, like a recovery biomarker believed to conform to what we call the classical measurement error model here. Now, using the sub-study data, we could estimate the true exposure on the full cohort by estimating X hat, which can be achieved by simply regressing the biomarker measure on the self-reported intake measure, X star, and the other participant characteristics. And this is our stage 1 model. So then in stage 2, we can use that calibration model with estimated nuisance parameters from stage 1 to estimate our exposure of interest on everyone in the study. And then the stage 2 model will be fit to that estimated exposure X hat and other covariates of interest to obtain estimates of the unknown regression parameter vector beta. So here's an example of what our stage 2 outcome model might look like when fitted using the plugin estimator we just outlined for stage 1, as well as other covariates in the example of logistic regression. So now I'm going to briefly introduce the sandwich estimator obtained by stacking the calibration outcome model estimating equations. So we'll let alpha be the parameter vector from the calibration model, and beta is the parameter vector from the outcome model. So we're interested now in theta, which combines alpha and beta. And then we'll define ui as the vector of stacked estimating equations that we form for theta, where u can be broken down into the estimating equations for the stage 1 model and stage 2 model. And then further, we'll define L1 as the log likelihood for the stage 1 model and L2 as the log likelihood for the stage 2 outcome model. You'll note that for maximum likelihood estimation, U1 and U2 are just the score functions, right? So the vector of first derivatives of the log likelihood function with respect to the parameters being estimated. So now we have the following stacked estimating equations. So then a sandwich estimator for the variance of our estimated parameter can be obtained by using this equation here. And this is typically called a sandwich form because we have the bread or the A component sandwiching the meat, which is the B component. And A is defined in terms of the derivatives of the score function with respect to the parameter vector theta, while B is defined as this bit down here. And this essentially requires multiplying the vector of score equations by its transpose. So now we can go into the general form for these A and B components in the two-stage regression setting. So first, we note that we're interested in a j plus k dimensional vector of parameters and of corresponding estimating equations. And A and B essentially have these general forms. So recall that A is just our matrix of derivatives of U1 and U2 with respect to alpha and beta. So the first thing to note is that the upper left quadrant of A will simply just resemble the Hessian matrix for the calibration model. And the bottom right corner just resembles the Hessian for the outcome model, the Hessian being the matrix of second order derivatives of the log likelihood functions with respect to the parameters being estimated. And next, you'll see that the elements of the upper right quadrant are all 0. And this is because the beta parameters are not involved in the estimating equation from stage 1. So the derivatives of these with respect to beta are all 0. Now, the trickiest part is the bottom left quadrant, and these elements are all non-zero, and that's because the plugin estimator X hat, which we introduced earlier, relies on the alpha parameters from the stage 1 model. And so this is, it looks a little tricky at first, but it actually can be computed fairly easily using numerical derivatives. And then beta, which is a little more straightforward to visualize, is just the stacked estimating equations vector times its transpose and has this general form here. And these elements actually don't require any specialized coding, and we can get the estimating equation pieces for any standard model fairly easily from software like R. Now, I did want to mention, speaking of software, that one barrier that I had found to applying the sandwich estimator in two-stage regression settings was the lack of available software to compute it without any customized or complicated statistical programming. So in our paper, we actually show that the sandwich variance estimator actually isn't too terrible to compute in standard software. And this is true for a large class of problems, including linear regression, outcome models, generalized linear models, and Cox regression. So in this paper, we show a very straightforward way to implement this approach in R using standard functions and regression outputs, which we've also combined all into one R package and one function called sandwich two-stage that can be applied to data from either a simple random sample or a complex survey design. So this little snippet of code here shows how we can actually give sandwich two-stage our function a few input pieces and allow it to calculate the sandwich variance for us. And so this is illustrated for the case of a simple random sample. So first we actually use a function from the survey package to specify the survey design, which is quite basic for the case of a simple random sample. Then we fit the stage 1 model in our calibration subset by regressing our measurement subject to classical measurement error, like a biomarker, for example, on the error-prone covariate measure and the other error-free covariates. And then we update our survey design to estimate that exposure on everyone in the full study cohort. Then finally, we fit our stage 2 model, which for this example here is a Cox model, where the covariates are the estimated exposure and the other covariates of interest. And then finally, we can use the sandwich two-stage function, simply taking as inputs the stage 1 model, stage 2 model, and a few names of variables in the survey design. And then we can apply the VCO function to get the sandwich variance, and we have our estimates. So that is the code piece of this, but I did want to show, just in a simulation study, how the sandwich variance is performing. And how it's performing in particular compared to competing estimators. So we did a numerical study designed to mimic a larger cohort study, fixing the sample size at 10,000 and the sub-study, the biomarker sub-study potentially at a smaller size of 450. And we'll consider a simple setting where we just have two covariates of interest, X and Z, which we simulate from a multivariate normal distribution. And we'll vary the correlation between these two variables, considering high and low settings. For our stage 2 model, we're going to assume a logistic regression model, taking this form and assuming the following beta 0, beta X, and beta Z terms. And then finally, we'll use the linear measurement error model to simulate the error-prone covariate, varying sigma, the measurement error variance, and we will simulate the biomarker measure in our subset to follow the classical measurement error model as shown here.
I'll let you know you have about 3 minutes.
Okay, thank you. Okay, so notice that, so here's just the simulation results, which I'll just show very quickly. I'm varying the measurement error variance in the leftmost column, as you'll see. And I'm showing side-by-side results for the low correlation and high correlation settings between the two covariates. And I'm showing results for the truth using the true unknown exposure, which we wouldn't have, of course, in real data settings, the naive approach, which is basically fitting the model to the hypothetical self-reported error-prone exposure, and then 3 regression calibration-based methods. The first showing the usual model-based standard errors coming out of GLM and R, and then 2 approaches for correcting the model-based standard errors, namely the proposed sandwich variance estimator and the bootstrap. And I'm presenting percent biases, median standard errors or ASEs, median absolute deviations, and coverage probabilities. And you'll notice in general, coverage is quite low for the model-based standard errors, indicating that we do in fact need to adjust for the uncertainty added by the estimation of the stage 1 model parameters. And the sandwich and the bootstrap do account for this extra uncertainty, but I wanted to point out that in settings like the high correlation one and high measurement error setting, the standard errors estimated by the bootstrap are almost always larger than the ones estimated by the sandwich and are too large, really, in some instances compared to their empirical median absolute deviations, reflected by the coverage probability that is too high. So overall, we're seeing that the sandwich is showing better performance in some settings, and as a bonus, it does require less computation time than the bootstrap. So the last component of this paper was actually data analysis, which essentially was a reanalysis of data from a previously published paper where regression calibration was applied to correct for covariate error. So the Women's Health Initiative, or WHI, was a collection of studies with the goal of investigating the major causes of morbidity and mortality among postmenopausal women in the US. And a previous publication reported incident diabetes hazard ratios for energy, protein, and protein density that were corrected for error in self-reported dietary intake. This paper used the standard bootstrap approach to account for the extra uncertainty, so we essentially intended to repeat this analysis, also applying the sandwich. So in the WHI analysis, I'll keep it brief because I know I'm running out of time, but we fit the stage 2 model with and without diabetes, just as Tinker et al. Did, and we compared the bootstrap walled and percentile confidence intervals to our proposed sandwich variance estimator. And I wanted to bring your attention to the example for energy intake, which I think really shows an instance where the bootstrap can lead to numerical instability. We obtained bootstrap standard error estimates of 37 for this example, corresponding to these implausibly looking confidence interval estimates. And generally speaking, for other exposures, differences between the sandwich and the bootstrap weren't as extreme, but we do see smaller standard errors on average estimated by the sandwich. So we found an instance where the sandwich can contribute. And just to conclude, we wanted to bring transparency to the sandwich variance estimator used for two-stage regression settings. And compared to competing variance estimations, we did see that the sandwich did have numerical advantages over the bootstrap and required less computation time. We've provided code and a package for applying this in R, which you can check out on GitHub. Future work, the package is only available on GitHub, so I'd like to put it on CRAN. The package can only currently handle one error-prone covariate, and we'd like to extend it to be able to handle other designs, specifically non-nested validation sub-study designs. And finally, I want to acknowledge that this is joint work with my dissertation advisor, Pamela Shaw, as well as Thomas Lumley. And you can check out our paper here, published earlier this year on AJE, and please check out our package on GitHub and let us know what you think. Thank you.
Great, thank you. So our next speaker is Dr. Sarah Pesco. Sarah Pesco is an assistant professor of biostatistics and bioinformatics and the director of the Data Science and Statistics Lab in the Aging Center at Duke University.
Thanks so much. Let's see. Are slides showing?
Yes.
Yes. Okay, great. Thanks so much. This talk is going to be a little bit more conceptual. Hopefully a quick breather from math, but there's a little. I want to talk today about missing data in EHR, which has been the focus of a lot of my work. But one thing that we've sort of figured out by dealing with a lot of missing data problems, particularly in EHR, is that many of them you can reframe as measurement error problems, which is something that we have much better handle on. We can think, as Lillian said, we can do regression calibration, we can do different kinds of adjustments for things. So if we can characterize these as measurement error problems, we have a lot more tools in our tool belt to handle missing data. Briefly, let's see. I'm going to give a quick introduction to EHR. Hopefully folks are very familiar with it in clinical research, but I'll give some background. I'll talk about what we mean by missing data in EHR. I'm going to introduce an idea called an informative visit process, which is plagued EHR clinical research for as long as we've been doing it. I'm going to show and hopefully convince you that this can and should be reframed as a measurement error problem, and then show you some future work that we've got going, hopefully in publication soon. So background, why EHR? Hopefully everyone knows this, but really it's an incredible source of data. Major opportunities for clinical research, broad range of data collection, huge patient populations. We can follow patients for many, many, many years, longer than a lot of cohorts, and it's relatively low cost because the data exists. Why don't we always do all of our research in EHR? Well, it has its own challenges. We have non-ideal measured factors. We don't get to pick what's measured. The study population is by default, not by design. And what I'm going to focus on today, which is incomplete data. And when we usually talk about incomplete data in the setting of a study, it's typically something we tried to capture, right? We tried to measure all of these visits. We tried to get baseline. We're trying to capture outcome measures. And we didn't capture it. We missed it. In EHR, it's kind of a weirder concept because there was no pre-planned, everyone comes in and gets, their blood pressure measured every day, et cetera. So when we think about incomplete data in EHR, a way that's kind of helpful to think about it is what's observed versus what's not. And the missing data or the incomplete data is stuff that we didn't see, but we could have or we should have. And that can happen for any number of reasons. I've given 5 here. You go to a different health system. Maybe your specialist is at a different hospital. And so one electronic health system does not have all of the information from all of your doctors. You relocate, you leave the area. You are really healthy. And when patients are healthy, they tend not to come into the doctor's office and get tests and labs done. Sometimes you come in and you have your regular checkups, but a lab wasn't ordered or a lab wasn't approved by insurance, so you don't have those lab values. And finally, if there's anything we've learned from COVID is that virtual medicine is great and does a lot of really wonderful things. If you are too sick or contagious and should be taking your doctor's visits from home, we can do that. But maybe we don't get all the same lab values or all the same metrics that we would have captured had you come into the office. And so what do we usually do with missing data? We characterize it. We say, what is the source of this missing data? Is it related to things that we've observed? Is it ignorable? Is it non-ignorable? Is it completely at random? We come up with a conceptual model that explains or at least characterizes our missingness. We come up with a missingness mechanism, and then we apply methods that we already know. We can use, regression adjustment. We can use imputation to impute missing values. We can use inverse probability weighting to upweight and downweight individuals who are more or less likely to have complete data, things like that. In order to characterize this, though, we need to know what data are missing, right? We need to know which subset of the population has missing outcome values. In EHR, that concept doesn't necessarily exist. What if we don't know that the data are missing? I'm going to go back to sort of the sources of missing data in EHR. And again, we're thinking about data that you could have observed but didn't. Do we know that a patient went to an outside health system? Probably not, unless we have a relationship with that health system and we share data. Do we know that a patient moved? Not unless they tell us. Do we know that a patient is very healthy and doesn't want to come in for regular visits? Not until you see them again, which is probably when they're feeling sick again. Do we know if a test wasn't ordered? Not unless a doctor left a note or it went in for an insurance claim and got rejected. And do we know if a patient is too sick to come in? Maybe we have a note for a virtual visit. Maybe we don't. The answer to this question, though, is we don't necessarily know that the data are missing. So what does that mean, right? We have many reasons or many sources of incomplete data in EHR. It's a unique challenge because we don't know what we don't know. And so we have to find a creative solution. Some of the work that I've worked with a few folks at Harvard and a few folks at Duke over the past 5 or so years is to reframe this as a measurement error problem. I'm going to walk you through an example and kind of how we're using it in practice. As I mentioned, one thing that plagues EHR is this concept of an informative visit process. This is a paper we did here at Duke on how and when informative visit processes can bias the inference you get when you're using electronic health records for clinical research. What do I mean by informative visit process? We mean that the likelihood that a given patient is seen by the health system or has an encounter or has observed data is associated with the underlying things we're trying to measure. Sounds like non-ignorable missingness. Is that a problem? You can probably guess yes, but I'll show you a little bit why. So suppose we're interested in studying the association between a biomarker and a particular outcome. You can pick your favorite biomarker, pick your favorite outcome. For example, we could say A1C and whether or not it's associated with surgical outcomes. Remember, in EHR, the data are by default, not by design. So we don't get to go in and test everyone's A1C right before they go in for surgery. What we do is we pull all of their labs for the past 5 to 10 years and get information about those patients. So we're actually only using the observed value, which, ta-da, is prone to measurement error, right? If it was very recent, great. We got a wonderful, very precise, excellent measure of A1C. If it was measured 5 years ago, probably far off. Is this a problem? All right, we have some measurement error. Sometimes that adds noise. We know that naturally happens. What if you add in an informative visit process? Patients who come to the clinic more frequently, who are more sick, or have diabetes or prediabetes, come to the clinic more often, they get their A1C measured more frequently. They're the ones who have the more precise and the more exact, more correct measure of their biomarker. Individuals who are healthy, non-diabetic, normal A1C, their last measurement was 5 years ago. So what do we end up with? We end up with differential measurement error that is related to the underlying measure you're trying to get. Turns out in this paper, in this specific scenario, you can actually correct for, this creates a whole bunch of bias, shocking. Measurement error causes bias. You can adjust for this particular phenomenon by adjusting for the frequency of your visits. It helps reduce it. It doesn't totally get rid of it. There's been some additional work on this. Some folks at Harvard, Glenn McGee's team, took this work, expanded and formalized this as a misclassification problem. And they've described sort of all the different ways that you can find this measurement error, this misclassification, and how it leads to bias. Between these two papers, we've shown that informative visit processes can be reframed as a measurement error problem. There are some things you can do to adjust for it, that you can look at this as misclassification. The McGee paper showed that actually bias can go in any number of directions. So what do we do in practice? This is a preview of some ongoing work with Knoop and Bavsar. We're looking at measurement error and bias implications by using multiple health system data, considerations for what happens if you can get validation data by either getting another health system data or by pulling in Medicare data and examining the information when you have Oracle data, what's the truth? Some really quick, probably not completely shocking results that we've already started to see if we're looking at the association between diabetes and different kinds of clinical outcomes. If you use data from a single health system, you underestimate the association between diabetes and heart failure. You gain a lot more information by getting that validation data or combining across health systems. You actually overestimate the association between diabetes and cardiovascular heart disease. Same thing for stroke. So characterizing this is sort of to show where this bias comes from, that it actually shows up in practice when we're doing clinical research, and that we can leverage outside data sources to build validation cohorts. We can use our, future regression calibration and other metrics to correct the biases that we get due to this measurement error. Quick recap. 2 papers we presented, feel free to take a look, and acknowledgements for the folks working on the Bavsar project right now. Thanks.
Thank you so much. And we do have time for a question if anybody has one in the Q&A, or I have one.
Sure.
This is super interesting and related to some stuff that I'm doing. So I wondered, you talked about combining like different health systems, and you talked about bringing in Medicare. I wondered if you've looked into like chart reviews as another form of supplemental information.
So we haven't yet. I think the big challenge with chart reviews is that it's so onerous, right? It's so much work. But now that we're starting to bring in large language models, that's something that we've started to incorporate, particularly with patient notes, to be able to abstract conditions, diagnoses, et cetera, from patient notes. I think that could be a really good way to support it. Again, I'm not sure how much you'll get from charts specifically that isn't already captured in EHR in a cohesive way, because you do still want to have reasonable capture across the patient population, and the charts are so highly variable. But if you can build algorithms that extract information from it, I think that could be a great source to add in.
Great. Thank you so much.
Thanks.
Great. So our next speaker is Dr. Grace E. Grace, are you here? Perfect. Grace E. is a professor and Tier 1 Canada Research Chair in Data Science at the University of Western Ontario in Canada.
Okay, so can you see my screen?
Yes. Would you like to full screen?
Okay, yeah,
Please?
Okay. Yeah, so thank you, Sarah, for organizing this session and inviting me to speak here. So today I'm going to talk something slightly different from measurement error. I will look at the measurement error issue in machine learning context. So this is a joint work with my PhD student and a colleague in computer science. So in here, I'm going to talk about the differential measurement error. First, I'm going to quickly use the framework. In supervised learning, usually each data point will be associated with a label, which is pretty much our response. And in image classification or speech recognition or other contexts, usually we need a large amount of labeled data. For example, in this screen, you can see we need to differentiate different objects on an image by labeling them as pedestrian, traffic lights, or vehicles, or even road. So in this situation, acquiring accurately annotated data can be time-consuming and very expensive. So right now, there is a practical way, which is called crowdsourcing. Crowdsourcing basically gives us an inexpensive and fast way to collect labels. So that is to use the internet information by collecting provided information or opinions from a large group of people via internet. And for example, if we look at the Amazon Mechanical Turk platform, it can give us hundreds of thousands of annotated data within few hours, and each from the entire world, and each label costs only a few cents. So this is fast and cheap. Which is the advantage. But the accompanying issue is annotators may have different knowledge or experience, so imperfect labeling skills will be coming into the play, giving us unavoidably noisy labels. In other words, our outcome will have measurement error. And in the literature, we have quite many reported information about this. For example, one paper reported corrupted labels could vary from 8 to over 30%. And for like brain image tumor data, it was reported 74 to 85% of segmentation errors. So this motivated us to consider a general framework. In here, I have an input, which is our covariates denoted by X, and our outcome, Y, which is called label, true label, which is unavailable to us. And the associated data is, for each input, we have multiple annotation, which means I use Y tilde, 1, 2, 3 until R to represent all those air-contaminated output information. So I'm using script D to include our available data. And we have a basic assumptions, which is feasible, which means each annotator will label our outcome independently. With this assumption, we can easily decompose joint distribution of the output information from our annotator into a product of two conditional probabilities. So the red part is called transition matrix, which is used to indicate the information about our misclassification in outcome. And the blue part represents a base model, which is something we are interested in. And our objective here is trying to use data with label noise to develop a prediction model, or in other words, we call it a classifier, which will provide us correct label for the future input data. And to do this, we have two components involved. First, we need the information about base model. And the second one, transition matrix, which is used to indicate the misclassification process, is involved. And in the literature of machine learning, people simply assume this instance independent model. In other words, in our statistical community, we call this is a differential measurement error. So here I'm going to look at a broadly situation. My misclassification could be instance dependent. In other words, I also want to consider a differential misclassification process. And the basic idea here is we start with trying to find anchor points. So what do I mean by anchor points? That means I want to find those data whose covariates X will have such feature. Conditional on this covariate, then the associated label or outcome value equals K will have a probability 1. If we are able to find these anchor points, then we can easily convert the conditional probability for misclassification of our output into the conditional probability of Y tilde given X. In other words, we can get around the no information about true label K in terms of observed label Y tilde of R. And once we are able to find such anchor points, we just group them with our associated labels, and then we are able to build our prediction model. And in this case, we simply assume all the anchor points would be independent. They could have a different distribution. So now my objective becomes I want to introduce a model to reflect our misclassification. And in this process, I want to reflect two main characteristics. There could be different effects from different annotators to reflect their varying expertise, indexed by R. And I also want to express potential dependence on the underlying grant truth of the true label value K. So with this ready, I want to introduce a conditional probability model by using deep neural networks. So essentially, I'm going to introduce a function little s, which depends on grant truth class label K and annotator R's information. In this sense, I'm going to introduce a certain soft max function which is given, so that the resulting expression will give me a conditional probability. So essentially, there will be two functions involved, psi1 of x and psi2 of x, which are unknown, and they have associated regression weights or parameters. So in this case, I'm going to use a deep neural network to describe each psi1, psi2 functions. Essentially, that means I'm going to specify a sequence of functions using a number of layers and a number of nodes within each layer and try to link all those given functions. And traditionally, we are going to consider saturated models by linking all possible nodes. And considering potential sparsity, maybe some nodes might not be connected. So we further introduce a sparsity indicator denoted by gamma. And we assign a certain prior distributions for this indicator to reflect possible available prior information. So here we use spike and snap prior structures to specify this prior distribution here. So this is the basic ideas of forming a way to learn our confusion matrix. With that ready, now we are going to consider 3 steps to estimate our conditional probability for observed outcome given true outcome. So the first step is try to use available machine learning techniques to train our base models so that we are able to find anchor points. With availability of anchor points, then the next step is we are going to use the posterior distributions to estimate our associated parameters in our deep neural networks that would be used to approximate our conditional distribution of observed outcome given true outcome and input. And finally, we can work out the estimate a sparse network for our transition probabilities. With this ready, now we are able to work out a posterior probability measure by using standard statistical techniques. And the first step is we want to see this procedure actually works, which means we establish its theoretical properties, and we found under our identified regularity conditions, then the learned noise models can be very close to the true transition models in Henninger distance. And our results is extended available works from IID settings to independent but non-identical distributed framework. So that is the first step, how to approximate our conditional probabilities under differential measurement error assumptions. Now the next step is how to do future predictions for new coming input by estimating a good labels. So the next part is we want to work out prediction models with label noise effects incorporated. So the basic idea here is instead of directly predict a label for a future input X from K possible outcomes, we're going to divide this problem into all pairwise comparisons. If I'm able to find 2 pairs of labels, I want to choose one best from these paired labels. So in this case, I convert problems into all pairwise comparisons. The problem becomes I'm going to select a label for the instance from 2 potential labels, K, K prime. So that means I'm going to choose the one best conditional probability out of the 2. So this essentially becomes a hypothesis testing problems. If I have 2 given conditional probabilities, I want to test one versus others. And this tells us we can use our traditional hypothesis testing techniques by comparing pairwise likelihood ratios. And here our likelihood is essentially the posterior distributions, which is labeled by different underlying true labels K or K primes. So this is essentially another problems of our statistical hypothesis testing problems. So this is the basic ideas of this project. We also established the like a Bayesian risk upper bound to characterize what how large or how small this procedure can involve the decision errors. So here I don't provide the details here, but to give you a quick flavor of these entire procedures, we are using some available machine learning data sets to compare our procedures. There are 2 data sets with human annotations. One is called Cypher10N, and another one is called Label Me. And we also consider 3 data sets with synthetic annotations, which means we artificially introduce potential misclassifications with different degrees, like 20, 35, 50% of annotation errors. And with these 5 data sets, we also compare the performance of our method with 15 available methods in machine learning communities. And for number 3, that is basically use the EM algorithms to address misclassification probability. So this paper was regarded as a first paper in machine learning field to look at label noise problems. So here we have 2 panels of graphs. The first panels indicate 3 different degrees of misclassification. We compare 15 available methods in terms of average accuracies. So the higher, the better. And the top red line segments indicates the performance of our proposed method. And the bottom panels include the reports the average estimation error for transition matrix. So that tells us how good or how bad our methods could perform in terms of estimating conditional probability of observed data given true data and the input. And the lower, the better. So our lines, our methods indicate the lowest line segments. So this simply highlights the good performance of our approach. So in summary, in this project, we explore challenging problems of learning with differential outcome measurement error process. In machine learning community, people call it instance-dependent annotations. And we introduced a Bayesian deep learning neural network to estimate transition probabilities. And we theoretically investigate the performance of our approach. And you may notice the essential idea centers on the availability of anchor points. What if there's no anchor points? What do we do? So generally speaking, we can extend our approach to some pseudo anchor point by relaxing the requirement of conditional probability y equals k given x equals value exactly 1 to something close to 1 by introducing some tolerance level delta. So this is the whole idea about this approach. Thank you.
Thank you so much. Great. So our last speaker is Dr. Li Tong, who is an assistant professor of biostatistics at St. Jude's Children's Research Hospital, where she also co-leads the biostatistics shared resource. So once you get your slides up, we'll be good to go.
Okay, are you able to see my slide? Let me put it on full screen. Okay,
Yes.
thanks. You're able to see it in the full screen format, right?
Yes.
It's my great pleasure to be here today. So what I'm going to talk about is slightly different. It's a little conceptual, in which that we want to revisit some of the conceptions or misconceptions that we have about misclassification, and hopefully that can promote some more detailed discussions about the underlying mechanisms. So before I move to the actual problem that we have worked on, I want to introduce the principle that myself have strong belief in. So to me, as a collaborative biostatistician, it's always important to motivate our statistical methodology development directly from a real-world data problem. And that's where in the development phase, that's where our theoretical and computational training kicks in. And after the new development or extensions, we should be able to apply that to the data which motivated us to do this. And in the past several years, I have been having increasingly stronger emphasis on this last component called disseminate. So I believe it's very important for any new method. There should be a user-friendly, user-accessible computational tool available for the users to access the method and to apply that to their own problem. So this work was motivated by our long-standing collaboration with CDC. As we all know, that CDC run a lot of national level surveillance studies, and those studies usually involve, by taking the HIV study as an example, involve at least a middle-size or sometimes very large sample size prospectively, and those participants, they were required to come back for regular visits, sequential measurements, and the questions are often sound pretty straightforward. For example, to evaluate the risk factors, their impact on developing certain clinical complications of interest. For this HIV positive or HIV negative but at risk cohort, a lot of infection or STIs, those are the outcomes of interest. But the drawback of such national level surveillance study is that due to the resource limit and sometimes to reduce the burden of participants, a lot of times the simpler but error-prone test had to be used for the practical reasons. So that's one of the barriers. So on the implementation side of such studies, we have seen that in the past over 10 years, the error-prone diagnostic tests are still very widely used, although there might be more accurate modern tests, for example, by taking bacterial vaginosis as an example, that culture tests, we all know it's more accurate, but it's more labor intensive. It may add more burden to the participants, so it's still not very commonly used. I'm not even mentioning like modern sequencing tools. So the misdiagnosis is usually not unavoidable in such studies. And from the methodology side, in especially in the epidemiology field, a lot of attention is still be given to exposure, to talk about exposure measurement error misclassification in cross-sectional studies like the snapshot of the study. And it always involves some simplified assumptions that everyone likes, that we can very easily borrow information from historical studies or external studies, assuming that we know everything about the performance of those error-prone diagnostic tests, and the information is transportable, and the error-prone rates, they are constant. They are not changing by time. They are not changing by patient subgroup characteristics. And in practice, there are some tools, but I have to say there is a lack of accessible functional tool that can be very easily and commonly used in the field still. So there are long-standing myths in the field. So historical data or external data are widely used to justify the current inference in the current study. And in nowadays, I think this is also related to a more trendy term, data integration. I believe in all the data integration problems, there is a central assumption there is that the parameters that we are talking about, we are borrowing information from, they should have similar characteristics, right? However, whether that is true or not in practice, sometimes it is very difficult to verify. And on the basis of this similarity assumption, there is a very well-known myth in the field is that if I just use historical or external oversimplified assumption, I know my results, my inference is biased. It's not consistent. However, this bias is safe because it is always toward the null instead of. In other words, scientifically, I'm becoming more conservative in making positive calls. And because this is based on a questionable assumption, so this belief is also very questionable there. So the goal of this the whole project, this is a long-standing project. We have many different components. So the overall goal of this project is to develop an end-to-end tool that is easy to use, can produce unbiased, efficient, consistent, and robust inference on those risk factor effects. And the two challenges there, misdiagnosed outcomes, and also people seldom talk about studies rather than cross-sectional studies. And two sub-goals, computationally easy, and also the inference, we have some requirements on that. So the approach, the design that we propose, this is joint work with collaborators at CDC, Yale, and also Emory. So the design we proposed is to just simply switch the integration from historical or external data to a random selected sample from the internal data. And we call this internal validation design. And there were other papers that I don't have time to share details that we talked about how to best select those validation samples, what kind of sample size is needed, how to make the inference more efficient. So the general idea is that, okay, now we are questioning the similarity of borrowing information from historical controls or external data. What if we just borrow information from ourselves? Then everything should be transportable, right? Everything should be similar. We come from the same cohort, same population. And on the basis of this design, and one is published and one is being submitted, that we proposed two inference approaches. And for those who are familiar with SAS, this percentage sign means that we put this, we convert this into a SAS macro, which can better suit the CDC needs, because a lot of CDC epidemiologists are more familiar with SAS than are. And those two approaches, one of them is based on the conditional inference, and I will discuss the main distinction in the next slide. And the other one is based on the marginal inference. So for most people in the stat discipline, this is not unfamiliar. When we have longitudinal data, of course, we can use like mixed effects model, which is actually a conditional model, conditioned on the random effects. Okay. In contrast, if we do not want to see this random effects, we want to make absolute estimate based on the marginal inference, then we can use marginal model. So that's the difference. And I also teach courses on some of those topics at the graduate school. And I think a lot of times there's a tendency that people interchange the use of the inference results from conditional and marginal models. And we always think the fixed effects estimates from conditional models, they should either be the same or very close to the marginal models. And actually, in this particular example, we see a departure from that. And I will give a very brief thought at the very end of this talk. And we also wanted to link our mismeasured outcome to the true outcome if we can, if we have a more accurate task that we can use to validate a very small internal subsample. Still, we can use conditional or marginal. We can even hybrid that. It doesn't matter. And here we are not putting constraints whether those covariates, they should be baseline or they can be time varying or longitudinal. They can be either. So the conditional model, the conditional inference came out first. The idea is not that complex, so we could use a parametric framework to jointly model the observations from both the internal validation sample and also the main study. And for the marginal model, then we have to use estimating equations, and I'm not putting details there, the derivative matrix and all that. And we also use sandwich estimator in the end. So those two, parametric or semi-parametric, they borrow information from the internal sample, they share the similar parameters, and we believe they offer the possibility for one to take a closer look at the underlying measurement error mechanism. The mechanism doesn't have to be a constant flat line mechanism. It can have much more flexibility there. And applying back to the HERS example, so I want to show that I'm not overstating that. For example, the error prone characteristics, the task characteristics is a constant. In fact, we see a lot of fluctuations in subgroups by taking the HIV, the sexual contact group versus the IDU group. You can see that the error rates are very different. It also changes over time. So at the end, we did some model selection there. Don't have time to talk about that. So at the end, I want to show you this slide. If we just ignore all the errors, we just pretend that I will just use whatever that I observed, definitely we can have some very misleading conclusion. For example, being HIV positive seemed to be a protective factor, significant protective factor. But if we knew everything in the truth, if we knew the truth, then it didn't have much effect there. And with both approaches, we were able to successfully restore the correct estimates and also the significance conclusion. And here I just want to make one quick comment. We always think conditional inference, marginal inference, interchangeable, but in this particular example, we saw that this might be very common, that actually the conditional estimates are slightly inflated compared to the marginal estimates. And we have a new master student who is going to look more into this. And this should be the last slide that we developed two parametric, semi-parametric approaches based on condition model and based on estimating equations. And this one is more favored by CDC because it's built upon a SAS procedure that they're familiar with for the estimating equation approach. We used IML, interactive matrix language. The sorted was a little complex, but still usable then. So I think I'm still safe to claim that we achieve our goals. Computationally easy. Maybe they would say IML is not that easy, but still, I think it's easy and the inference is consistent and robust. Okay, I think I'm almost time, and that's the end of my presentation. And thanks for being here.
Great. Thank you all. So quickly before we transition, Grace, can I ask you, can we take a quick group photo and then we'll let the next group of speakers come in? Is that okay? All right, everybody. 1, 2, 3. Thank you. Thank you all
Thank
so much
you.
for
Thank you.
participating. I really enjoyed this, and I'm sure the audience